Shoot a single electron at a barrier with two narrow slits, and it doesn't pass through one slit or the other. It seems to pass through both simultaneously. The interference pattern that builds up on the screen behind it is the unmistakable fingerprint of a wave of possibility spreading through space. Yet the moment you install a detector to see which slit the electron actually used, the interference pattern vanishes. The electron becomes a particle again. The active observations seem to collapse the quantum possibilities into a single, definite outcome. Physicists noticed something deeply strange. The world at the quantum level appeared to behave differently depending on whether it was being observed. That wasn't just surprising, it was philosophically catastrophic. At the heart of this strangeness sits an object called the wave function. In quantum mechanics, the wave function is a mathematical description of a particle's quantum state. It contains all the information about what a particle could be, every possible position, every possible momentum, encoded as a set of probabilities. When nothing is measuring the particle, the wave function evolves smoothly and predictably, spreading and interfering like a wave. But the moment a measurement is made, the wave function appears to collapse. All those possibilities vanish, and only one outcome remains. The question physicists have wrestled with for nearly a century is deceptively simple. What is the wave function? What does it actually represent? There are two broad camps. The first says the wave function is a real physical thing. It isn't just a calculation tool. It describes something that genuinely exists in the world, a physical wave propagating through reality. On this view, the collapse of the wave function is a real physical event, something that actually happens to an actual object. The second camp says the wave function isn't a description of reality at all. It's a description of knowledge. It represents what an observer knows or can know about a system. When the wave function collapses, nothing physical happens. What changes is simply the observer's information about the world. These two positions lead to radically different universes, and the debate between them has never been fully resolved. Because hidden inside both of them is a question that physicists have quietly avoided for decades. If the wave function depends on observers, what exactly counts as an observer? And does that mean reality itself depends on who is looking? In 2019, a team of physicists turned that question into an experiment and produced a result that shouldn't have been possible. They constructed a scenario based on a thought experiment originally proposed by Eugene Wigner in the 1960s. Wigner imagined a physicist, his friend, performing a quantum measurement inside a sealed laboratory. The friend measures a quantum particle and gets a definite result. But from Wigner's perspective, standing outside the sealed lab with no access to the result, the entire laboratory, his friend, the particle, the measuring equipment, everything, remains in quantum superposition. The friend has a definite experience. Wigner's description says no definite experience has occurred yet. When the 2019 experiment put a version of this scenario to the test, using photons and carefully controlled quantum systems, the results confirmed something extraordinary and disturbing. Two observers, following the laws of quantum mechanics perfectly, arrived at contradictory conclusions about whether a specific event had occurred. Not different interpretations, not different approximations, logically contradictory facts about the same physical event. The researchers concluded that if quantum mechanics is universally valid, then objective facts, facts that hold true for every observer regardless of their position or perspective, might not exist. Read that again slowly. If quantum mechanics is correct, there may be no single objective reality that everyone shares. And yet, here you are. Here we all are, living in what certainly seems like a shared world, agreeing on the color of the sky, watching the same sunrise, pointing at the same mountains. If quantum mechanics allows observers to have contradictory realities, Why does the large-scale world feel so deeply, stubbornly consistent? That is the question that led physicists toward one of the most provocative ideas in modern science. The theory is called quantum Darwinism. It was developed primarily by the Elmse physicist Wojciech Zurek, working at the Los Alamos National Laboratory, and it proposes something that at first sounds almost too elegant to be true: reality. As we experience it is the result of a selection process, not natural selection acting on living organisms, but something analogous acting on information. Here is the key insight. When a quantum system interacts with the environment around it, and in the real world, every object is constantly being bombarded by photons, air molecules, and radiation. It doesn't just interact once. Information about the quantum system gets copied into the environment over and over again in countless fragments. Each photon that bounces off a chair carries away information about that chair. Each air molecule that collides with a surface carries away information about that surface. The environment becomes a kind of vast, passive recording medium, perpetually copying information about the objects embedded in it. Now, here is where the Darwinian logic enters. Not all quantum states can be copied efficiently. The quantum properties that transfer reliably into the environment, that can be imprinted consistently across millions of different fragments of the environment, are the ones that survive. They become redundant. Multiply represented. Any observer who samples even a small piece of the environment, even a single photon reflected from an object, receives the same information about it. This is why when you and a stranger both look at the same tree, you both see a tree standing in the same place. You're not exchanging information with the tree directly. You're both independently sampling the environment, which has already been saturated with copies of the same information about the tree. The shared reality you experience according to quantum Darwinism is not fundamental. It is the residue of a selection process. It is what's left after the environment has ruthlessly filtered quantum possibilities and amplified only the most copyable, most redundant, most stable states. Reality, in this framework, is the information that survives. The implications begin to sink in slowly, and the more carefully you sit with them, the stranger they become. Think about what this means for the objects you see around you. They don't have definite properties because the universe is fundamentally classical. They have definite properties because those properties can be encoded into the environment efficiently enough to be sampled by multiple observers. The solidity of the chair, the color of the wall, the shape of a face, these are all selected properties. They are the quantum states that won a competition for redundancy, for copyability, for survival in the informational landscape of the universe. The properties that didn't win, the genuine quantum superpositions, the interference terms, the strange entangled states, they're still there in principle, but they're so fragile that any interaction with the environment destroys them instantly. They leave no copies. They leave no trace. They don't make it into the environmental record. So, no observer ever sees them, and they play no role in what we call everyday reality. In a very precise sense, the world you experience is not the world. It is a projection, a curated broadcast, the most stable signal emerging from a vast quantum noise floor, amplified into apparent existence by the sheer redundancy of information copying. But not everyone is convinced, and the criticisms of quantum Darwinism cut to something deep and uncomfortable. The central challenge is this: for the theory to work, you need to define what counts as the quantum system and what counts as the environment. The system is the thing being observed, the particle, the cat, the chair. The environment is everything else: the photons, the air molecules, the vast surrounding world. But in quantum mechanics, everything is connected. There are no clean boundaries. Drawing a line between system and environment is not a fact about nature. It is a choice made by the observer doing the analysis. And if the theory requires someone to make that choice before it can explain how observers come to agree on a shared reality, then the theory may be secretly assuming the very thing it is trying to explain. It is invoking a perspective, a point of view, to explain how perspectives arise. It is drawing on the concept of an observer to explain why observers exist. Critics argue this is a subtle but devastating circularity. The explanation may be incomplete in a way that cannot be patched. Zurich and his collaborators are aware of this challenge. The work continues. But the honest answer, as of now, is that no one has fully closed the loop. The emergence of classical reality from quantum mechanics remains one of the deepest open questions in physics, and every attempt to answer it seems to reveal new layers of the problem underneath. There is something quietly vertiginous about where this leaves us. We began with the assumption that the world simply is. That reality precedes observation. That the chair exists, whether or not light bounces off it, whether or not anyone looks. This assumption felt as solid as the chair itself. What quantum mechanics has done? Across a century of increasingly precise and increasingly strange experiments, is systematically hollow out that assumption. Not by proving it wrong exactly, but by revealing that it may not mean what we thought it meant. The definiteness of the world, the sheer stubborn there-ness of things, may not be a feature of reality at its deepest level. It may be a feature of information flow, a feature of which quantum states can be copied efficiently enough to establish consensus across observers. Quantum Darwinism, at its most ambitious, suggests that reality is less like a canvas and more like a broadcast, less like a fixed stage and more like a signal that keeps reinforcing itself through repetition. What you call the world is what survives the filter. What you call an object is a pattern stable enough to leave consistent impressions across the environment. What you call existence may be, at the most fundamental level, a form of persistence, the ongoing success of certain information patterns in propagating themselves through a quantum universe. And here is what no equation can fully dissolve: the unsettling sense that something important is missing from this picture, because somewhere in all of this, in the wave functions and the decoherence and the environmental copying and the redundant records, there is still you, an observer, a point of view that experiences the world, not merely samples it, a consciousness that doesn't just receive information but notices it. And quantum mechanics, for all its precision, has never explained what that is or why it should exist at all. Maybe reality is the most stable pattern of information that the universe can sustain. Maybe what we call existence is what survives the relentless process of quantum selection. Maybe the world you wake up to every morning is not a given, but a result. The end product of a filtering process running at scales you will never directly perceive. Or maybe reality is stranger still, and the story we've told ourselves about information and observers and emergence is only the beginning of a much deeper mystery. One that physics has uncovered, but not yet learned how to hold. The universe kept it secret for 14 billion years. We've only just begun to ask the right questions, and the answers, so far, are not reassuring. They are beautiful and precise and deeply, profoundly unsettling. Because if the physicists are right, you are not living in reality. You are living in what reality chose to show you, and what it chose not to show you, that remains, as it always has, completely invisible, perfectly hidden, quietly real.